Log on, tune in, find out. Another good idea from Cambridge.
Right here. Okay, great. All right. Yeah, so I was busy, but I have been introduced, right? So thank you. Thank the organizers. I would like to thank the organizers for inviting me. So I'm going to talk about seismic inverse scattering by reverse time migration, which is joint work with Tim Oppetroot, who was a PhD student who is now graduated, and with Martin de Hoop. So we're talking about the familiar seismic imaging problem, which you see a cartoon here. We're basically, so here there's wiggles, but the projector is not really showing them. So basically we're connecting two developments. One is in the seismic literature. It's about reverse time migration, and even earlier the Klaarbout paper about seismic imaging using using downward continued wave fields. And the reverse time migration was developed around this time around 1980, and but recently it has become a lot more popular because it has become feasible. It is a very expensive procedure. And the second development is the mathematical treatment of seismic imaging as a linearized inverse problem, and that started with the paper of Belkin and a little bit later Rakesh and several other. Of course there has been a continuing line since then, and that basically shows that migration procedures are some form of a linearized inversion procedure. And today we connect these two developments, basically showing that RTM can also be formulated as the solution to a linearized inverse problem in an appropriate microlocal sense. So let's look at the linearized inverse problem. Because here we have the wave equation with a point source in space and in time. We linearize this. We assume there's a smooth background Cx, and we linearize around this background, and I call the reflectivity R. So this smooth background, we solve the wave equation, we get a source field, which is the refracted waves. Basically there's no reflections yet in there because the background is smooth, and then these reflected waves are modeled by the linearization. You get a second term, which is the scattered field U, and that satisfies the wave equation again, but now on the right hand side there's the product of the reflectivity and the source function. And well, these other terms 2 over c squared and the time derivatives, they are also there, but they're not really that important. It's really the product of the reflectivity and the source that is most important. So we consider this in the usual setting where the background is assumed known. So the usual setting for analyzing migration algorithms. And the medium is considered unbounded. That means that at the top we have this boundary, but this is assumed to be removed. This is realistic with current processing, and it's always done. Okay, so the inverse problem becomes to determine this function r of x from the data, and the data is assumed to be u. So there's these direct waves are assumed to be sort of in a different part of the data, or they're assumed to be suppressed. So we invert from the scattered field, and that is measured at the surface of the domain. So x3 is 0, and then some subset of the x1, x2 coordinates. So some subset of the surface, and some subset of the time interval. So it's a linear. This is a linear map from R to U. So it's a linearized inverse problem. Okay, so reverse time migration. Here there's a sketch of the procedure. You compute the source wave field from the background and the source, and you compute the second wave field, which is the reverse time continued receiver field, and I will give a more detailed explanation in just a moment. And then you apply so this reverse time continued receiver field basically computes the receiver field, computes waves inside the medium from back propagating from the surface. So you construct the scattered field, the scattered wave field. You reconstruct it. It's not exact. You will see the differences, but yeah, it's a familiar principle that you back propagate waves. So the imaging principle states that that reflectors exist where where the source field and the back propagated receiver field are time coincident, and that has been translated to formulas. These formulas combine these two fields into a formula for an image I of x. This is one formula where you just take the correlation of the two in time, and a second formula is over here. This formula, you transform the equation to the Fourier domain, but instead of multiplying by the adjoint of G, you divide by the source field, and that gives a different normalization of the image. And we'll do something similar than this to actually get an image. So those are two well-known methods, and for example, for the first one you can already analyze from known results that you get a pseudo-differential operator times the reflectivity for the image. So this is okay. So now let's go to the main result, which I put right in the beginning here, which is our main result. Then the rest of the talk will be more about the explanation. So we define the UR field as a anti-causal solution, which means that the solution is going to be zero after a certain final time. So it's a final value problem. It satisfies a wave equation with a source, and the source is located at the surface by this delta function. The data is this scattered field in the surface. X prime is the coordinate in the surface, and we cannot inject it right away. We need some factor, and this is a pseudo-differential operator that has basically two components. One is a sort of normalization over here, and the other one consists of pseudo-differential cutoffs. For example, you have to regularize near the boundary of the acquisition domain, because if you don't use a nice cutoff, you get an additional singularity and you get artifacts in your image. So you have to combine this factor with some pseudo-differential cutoffs, and that is the source in your wave equation for the reverse time continuation. Okay, so this is the way you get the UR, and then the question is, how do you combine the source field and the UR field? And that is given over here. So what you see is these terms are together the ratio imaging condition of Klaarbout. What we've added is a term that involves the gradients of this source field and of the back-propagated receiver field. So what this will do is that depending on the this is, of course, you interpret this in a geometrical optics sense, even though you don't compute any geometrical optics. Right? So you know you have an incoming wave that has some arrival direction, a reflected wave that has a takeoff direction, and you back propagate it. And this will give you an angular dependent factor that will be necessary to really get an inverse instead of just a sort of a picture that is maybe structurally the same but not quantitatively. So you have a factor that depends on the angle of the reflection angle. So what's notable about this is that this factor, that if you look carefully at it, it becomes 0 for direct waves. So that is an important property, as I'll explain later. Okay, and what we find is that the image, that singularities are reconstructed in the reflectivity. So the image is microlocally equivalent to the reflectivity. Okay, so this is the result. And what do I tell more about it? So I have a part about constant coefficients, which is a motivation how to get this formula for the image. So I make some remarks about the proof. And we have some numerical examples which are so of a very simple nature, but we already in this very simple examples, this is a high frequency theory, so already in these very simple examples you don't get exact reconstruction, so it's sort of interesting to see for finite frequencies what you get. For finite frequencies in the situation that you in principle can reconstruct. Okay, so turns out this imaging formula can be you can sort of guess it based on a constant coefficient problem with a plane wave source. So here you have such a problem, a wave equation with a plane wave source multiplied by some unknown function or by the reflectivity function, which is the one, well, first we assume it's known, but then we're going to invert and reconstruct it. Yeah, to solve such an equation with constant coefficient, you can of course just go to the spatial Fourier domain and you get a formula for the scattered field. Now this is a very nice formula because it shows you exactly the relation of the Snell's law, the relation between incoming and reflected fields, and the reflectivity in terms of the wave numbers. So here you see the wave number of the outgoing wave, that is just psi. Then the incoming wave must have the same wave number of the same length, but it points vertically downwards, so that is 0 psi in this 2D picture. And then the reflector wave number is in here, and it's just the difference of the two. So yeah, with the geometrical optics in terms of wave numbers. So this formula, it turns out the reflected field, we assume we have this time reversed field is now taken from a snapshot, so from a time is constant situation. So this is a simplified problem, so we don't assume an acquisition surface, but we just assume we measure at some time after the scattering, we measure the wave field and we backpropagate it. And if you do that, you get this formula for all time, and the original formula was valid for time such that the source has passed the support of the reflectivity. So they're not the same, but this formula has just a bigger domain of validity. Yeah, so now, okay, the question is how do you invert this and get R from this formula? So you do this in 2 steps. First, you know that you have this imaging principle, and just let's try it and just say, okay, we just take U at the time where the incoming source field passes. And that's the first step, but that is this one, but that's not enough. Let's compensate for some amplitudes, and this guy we will use, it turns out we need it, and it becomes clear why. So if you do this, you get you just insert it to get a formula with the Fourier transform still present, and it's yeah, you have this wave number, Fourier number, and what you do is you do a change of variables, and then these factors yield wave numbers, and that's exactly the Jacobian, and you get reconstruction. You get an inverse Fourier transform, and I cheated a little bit because you can't invert from the direct waves. So the inverse Fourier transform is not over the entire domain, strictly speaking, around psi 3 equal to 0, you have a problem which corresponds to direct waves, so waves that are reflected and not really reflected. And now this formula, so this we sort of guessed it from the imaging principle, and indeed it turns out it works, except for these direct waves, which you know are not are an issue anyway. Now we have to transform this to a formula where we use the source field and the receiver field, because we're not supposed to use the arrival time with the source field. And okay, we use that the arrival time is x3 over c, and this we go to the Fourier domain, and the source field looks like that in the Fourier domain. So this vector is just obtained by taking the gradient of the source field, and in this way we get the gradient of the source field in there, and we have this expression. Okay, so it's a constant coefficient analysis that gives you the imaging condition. However, to prove that it's good, of course you have to go to the variable coefficient case, right? You have to show that well, first you have to the variable coefficient case, you treat it as locally constant. It is that you had it's this idea of high frequency asymptotics. And the second part is that in this variable coefficient case, what you find is that these kind of integral expressions, they may lead to constructive interference and to large contributions, and you have to argue that these are absent, and that leads to a number of assumptions. So okay, so I was going to say a little bit about the tools we use for the variable background, that is microlocal analysis. So I guess it's familiar to many in the audience. Basically we're reconstructing singularities. You know, there's this notion of singular support that tells you the location. Well, we need a little bit more, which is the wavefront set, which is a set of pairs of position and orientation that tells you that you can derive about the singularity. For example, if you have a discontinuity, the orientations are along a curve, the orientations are normal to the curve, and you can define this as a decay of a Fourier transformed and localized function. You can properly define this. For example, you can find this in the books of Hermander and Duistermaat. We use Fourier integral operators which have a kernel of this form, an integral of oscillatory functions, pseudo-differential operators, of course, and these Fourier integral operators, they have a very nice description in terms of how they map singularities. So if you know the position and the orientations of the singularities, and you know the Fourier integral operator, so you know the input singularities and you know the Fourier integral operator, you get the output by a geometrical map, and that is connected to ray theory, and yeah, it's applicable to wave equations, for example. So for wave equations we use local Fourier integral operator solutions, which are integrals of WKB solutions, but for globally we managed to avoid the more complicated Fourier integral operator. We managed to avoid the explicit expressions. We just use propagation of singularity and time reversal at the microlocal level. So we managed to avoid like these Maslov type wave phase functions. Okay, there's one. Yeah. So there's basically, to analyze this, what you see here, we need an additional field for the analysis, So this picture sort of simplifies the scattering. Here we have a surface and a source. This is the spatial plane, and this source field, let's say the source field contains a downward propagating wave. Of course it will, in reality there are many arrows, but let's take one of them. And suppose we have a reflector, then we get a scattered field. Now this reverse time continuous field contains this, what happens is scattered field arrives at the surface and then you propagate it backward, and maybe there's a second part of the wave field that is mapped outside the acquisition domain and is not propagated. So what you see is that this acquisition suppresses a part of the scattered field in the time reversed field, and you also see that this time reversed field continues below the reflector. And what we introduce is an additional field which continues below the reflector, but which doesn't have this suppression that comes from the acquisition. And then we relate the, let's say, we go from two steps from considering imaging from this, and then, which is not possible because it's a physical field, and then we relate those two fields and see how that propagates to the imaging formula. So that is basically the proof. Yeah, I guess we've got all of it, the Fourier integral operator techniques, these fields. And yeah, for example, we get an explicit expression for a local explicit expression for this continued scattered field, which is this intermediate field. And we understand the canonical relation in terms of the rays, which is, yeah, it's like you encounter in analysis of Kirchhoff migration. Yeah, what do we see? Let's see. The effect of the acquisition set when you look down below of this time reversed field is the suppression of part of the field by a pseudo-differential operator. Yeah, to understand this, you have to split this time reversed field into two parts with positive and negative frequencies, and then each of these parts contain you get a pseudo-differential operator that suppresses that part of the field due to the acquisition. Yeah, well, and in the final image you basically see the reflectivity with part of the field suppressed, which is exactly those parts that you can't see. So here you see a wave number, a position, x and zeta, and an incoming source ray. And if this goes, the reflected ray goes to the acquisition, you can see this x and zeta, and the symbol is 1, and otherwise it's 0. And in fact it's the cutoff at the surface that's transported along these rays down to this x zeta. Okay, so let's look at numerical examples. We've taken some, this is a gradient medium, it's just linearly increasing in depth, and we took some wave packets that are inside that are in principle visible, and the rays are such that the source is over here, and the rays are such that the reflected rays are such that they end up in the acquisition, which is from here to there, and a little bit outside, because there's also a large cutoff involved, or with a very slow cutoff. This is the velocity perturbation, and this is the reconstructed velocity perturbation. And yeah, well, what you see is familiar in these images. You see some artifacts that is the resolution in this parallel direction, or is not so good. You see, but it's very small because we did a very careful tapering for the data, and well, we found some errors that if you compare some traces, you get some errors in this range. But again, this is very so this is sort of interesting because this is clearly a situation where the theory should hold, but you still get well, what we would yeah, maybe this is a small error in astronomy, but in mathematics I would say it's a big error. So, and the second example is a bit like it. except we took a low velocity zone leading to caustics. So this is from the projector. This continuity. You see the caustic here. Yeah, and you see it's perfectly reconstructed even in the presence of caustics. And the condition is that caustics are not allowed between the source and the reflection point, but they are allowed between the reflection point of the receiver. And this was just an example to verify that. And here you see some the caustics in the source field, and they lead to errors because you divide by the source field. And these caustics lead to very small values of the field, because you have multiple waves interfering. Yeah, so caustics between reflector and receiver are not a problem. Okay, so we modified reverse time migration to become a linearized inverse scattering method. The main result is a theorem about this. So what's interesting also is that I said this new condition leads to an angle-dependent factor that's 0 for direct waves, and it turns out that that's exactly what you need to suppress low-frequency artifacts that have been observed. So these artifacts correspond to scattering over 180 degrees, so basically a direct wave, and our factor exactly suppresses that. So that's a nice feature, that by doing it right you get this, you suppress these things. Okay, and that's it. Thank you for your attention.
Any questions? Could you just say again what you assumed about the background C in your theorem?
So there's no caustics between the source and the reflection point. That's one. So this one is a bit, it becomes from the way we so there's no direct waves, okay, and then there's another one which is that once we're above the acquisition level we don't return to it, because we inject this source by a delta function times data, and if we do this, you get 2 times the data down here. So this is not allowed. But typically, in typical examples, this is unphysical anyway. Say you're at the C, right? This is constant and everything is straight. Or there is a PML layer.
Degree of smoothness?
Degree of smoothness, it's C infinity. So it's exactly like the Balkan setup, right? Except we do it for RTM.
Okay, I think we'll try and get back on track, and thank Chris again.